Okay, so as we already know that, so, so we know that so if a function f is let us say holomorphic, because we have seen that they both are equivalent. Can you just mute your mic, Minal? F is analytic at z naught. So then basically fz can be written as, can you please mute yourself? So in the to the power n, which is valid in some neighborhood of z naught. Sorry, z minus z naught to the power. Okay. So in this section, we will see that basically, if f is analytic in an annulus, it can be written as a double power series. Uh, so let me write it down the theorem. Okay. Before that, let me introduce some notation. So I will say an annulus, which is, so I will denote it by, just wait a minute. So I will denote it by, let us say, z naught, z naught, r1, r2 by z belongs to C, such that mod of z minus z naught is greater than r1 and less than r2. Okay, so this I will denote as in, so where r2 is greater than r1 and r1 is greater than equals to 0. Okay, let us recall this theorem. It says that, so let f be analytic in the annulus. Let us call it as, so annulus, let us call it as whatever it is, g, that says that z naught is greater than, let us say, r1 and r2. So then fz is basically summation. Fz can be written like this: an z minus z naught to the power n. Okay, where this convergence, where the convergence is absolute and uniform. So this is absolute over basically, that says that where your basic r1 is, small r1 is, okay. Also, so this an can be calculated by this 1.2 pi I TL over gamma f upon z minus z naught to the power n plus 1 dz. Okay, so this is the expression where gamma is the circle, mod z minus z naught is equals to r for any r which is in, obviously in this one, so which is in r. So r is basically r1 to r2, and moreover this expression is unique. Okay, moreover this is unique. Okay. So I mean uniqueness one can easily prove this one. You just have to consider that it has two expressions. I mean suppose fz is something n equals to minus infinity to infinity en z minus z naught to the power n, which is also equals to some other series expansion. So we'll say bn z minus z naught to the power n. So your claim is an is equals to bn. Okay, so this is the meaning of uniqueness. So I mean, let us one can try to prove this one. So the series is valid in, so the series is valid in mod z minus z naught is greater than r1 and less than r2. Okay, and let r1 is less than r is less than r2. Then each of both of this uh, series converges uniformly on this curve is equals to r. Okay, so what we need to do is, so for any integer, so for any integer k, what we're going to do is multiply by 1 upon 2 pi iota z minus z naught to the power k. Okay, so this is basically, so at the place of n we have to multiply this with this one in the both sides. So summation n equals to minus infinity to infinity an, so an upon 2 pi iota, and what we can do is, so let us take over gamma z minus z naught to the power n plus k dz, and similarly here we can write infinity bn upon 2 pi iota integral over z minus z naught to the power n plus k dz. Okay, so now since 1 upon 2 pi iota integral over gamma z minus z naught to the power m dz is basically 1 if m is equals to minus 1 and 0 otherwise. Okay, so I mean if if n plus k is minus 1, that is that is n is equals to minus 1 minus k. So this implies a minus k minus 1 an is equals to b minus k minus 1 for each k belongs to this integer z, and this implies ak is equals to bk each k. This means that the sage expansion is unique. Is it clear? I mean, yeah, but keep in the mind that once you change this annulus, this may have different representation. But in the fixed annulus, this representation will be unique. Okay, let us try one problem. So any doubt in this one? Okay, so which of the following statements are true? Following statements are true. So first one is the also so this one is known as the Lorentz-Sage expansion around Z naught. Okay, so this is called Lorentz-Sage expansion of F around Z naught, or you can say about Z naught. This expansion of the function f of z is equals to 1 upon 1 minus z on, so this is d minus 0. So this d means unit disk, means z such that mod z is less than 1, has non-zero coefficients with negative indices. Second is again the same thing, the Lorentz series expansion of z is equals to 1 upon 1 minus 1 z in punctured unit disk coincides with the power series summation n equals to 0 to infinity z to the power n. Okay, now third thing is on the annulus z belongs to c, so z mod z is greater than 1. So observe that here this, so in this we can also consider R2 can be infinity also. In this annulus, this one, the function on 1 minus z has the Lorentz series expansion summation n equals to minus 1 to infinity z to the power n. Okay, and the fourth option is the Lorentz series of the function f z is equals to 1 upon 1 minus z is unique is unique unique irrespective of the annulus z. Okay, so this we need to check. Let's look at the solution. So the function is basically from the punctured unit disk to C, which is defined by fz is equals to 1 upon 1 minus z. Okay, so clearly f is analytic. Again, set such that mod z is greater than 0 and less than 1. So in this annulus centered at 0, it is analytic. Now it has a Lorentz expansor. So f has which is, we can write it as in general form z to the power n. Okay. Now what is the formula for this coefficients? So an is basically 1 upon 2 pi iota integral over gamma fz upon z to the power n plus 1 dz. Okay, so where gamma is any circle, mod z is equals to r, r is in between 0 and 1. Okay, so this is nothing but iota integral over gamma. So this will become dz upon 1 minus z into z to the power n plus 1. Okay, so let me write it again so that integral over gamma dz upon 1 minus z into z to the power n plus 1. So if n is greater than equals to 0, okay, then what is this an? So this an is basically nothing but n factorial, which is nothing but always 1. Okay, and if n is negative, so an is basically 1 upon 2 pi iota integral over gamma dz upon 1 minus z into z to the power n plus 1. So if n is negative, n plus 1 is also will be less than, just wait a minute. Yeah, so if so basically it means that n is less than equals to minus 1. Okay, so this z to the power n plus 1, so n plus 1 will always be less than equals to 0. Okay, so this z will be z to the power n plus 1 will, once you take to here, so this n plus 1 will always be less than 0. Okay, now you take it to the uh, numerator, so this will becomes an analytic function. Okay, now this is your curve, so this will be 0 by cosine by Cauchy's theorem. So, so this is 0 for every n negative. Okay. So if you see the, so it is written that the Lorentz expansion of this function on this one, on this annulus, has non-zero coefficient with negative indices. Okay, but but for negative indices we are getting it is always zero. So this option is not correct. Okay. Now second is, so the Lorentz expansion of this one, this coincides with the pulses this one. Okay, so once this is zero, what is your f z? It is nothing but, so an is your 1, so this you will get summation n equals to 0 to infinity z to the power n. Okay, so option 2 is also true. So option 2 is true, 1 is false. Now let us look at this, uh, the Lorentz expansion of f in this annulus. Okay, so now consider the annulus. Z belongs to C such that mod Z is greater than 1 and less than infinity. Okay, so this we need to consider now. So clearly f is analytic, analytic in this annulus. Okay, so f has Lorentz series expansion. Lorentz expansion around z equals to 0. So we can write it as fz as infinity to infinity a n z to the power n. Okay. Now, what is your an? An is nothing but 2 pi iota integral over gamma fz upon z to the power n plus 1 dz. Okay, where the gamma is the curve mod z is equals to r, where r is greater than 1. Okay, is it clear? So now what, let us say what is a naught. So 1 upon 2 pi iota integral over gamma fz upon z dz, which is nothing but 1 upon 2 pi iota integral over gamma dz upon z into 1 minus z. Okay. Now this one can write it as 1 upon 2 pi I and integral over gamma dz upon 1 minus z plus integral over gamma dz upon z. Okay. Now clearly this a naught will be 0. Is it clear? How this a naught will be 0? Can you tell me? So this gamma is basically r. Any r you can take. So you can just take r is equals to 2, whatever you want. So now can you tell me how this one is 0? Okay, so you can go through and check this one. So this a naught is equals to 0. What is the option now? So third thing is, uh, so third option is not correct, because if you see, it is saying that a 0 is 1. but that is not the case. Okay, so this is not correct. Also, the Rollinson expansion of this is unique irrespective of the annular center at 0. It means that now once we have seen in this annulus we have seen that what is your A naught. A naught is 1. Okay, in this annulus A naught is 1, but in this annulus A naught is 0. So means Lorentz expansions are different. Okay, so this is also not correct. So is it okay? Any doubt? If you have any doubt, you can just let me know. So no doubt, then we'll move towards the next thing. Now we'll talk about singularity. Okay. So point Z naught is said to be a singular point of f, or just singularity of f if f is not analytic at z naught, but every neighborhood of z naught contains at least one point, contains a point at which f is analytic. Okay, so this is the definition of singularity, and we divide singularity into two parts. One is isolated and one is non-isolated. So isolated singularity. Okay, so z naught is isolated singularity. So z naught is isolated singularity of f if if there exists a neighborhood of z naught in which f is analytic throughout. So if there exists a deleted deleted neighborhood of z naught such that f is analytic in that neighborhood. Okay, I mean, for example, you can see, like, for some examples, if we say sin z by z at z equals to 0, so this has a removable singularity. Sorry, this z equals 0 is isolated singularity. Fz is, let us say, 1 by z, so at z is equals to 0, this is again isolated singularity, or you can take, let us say, f3 of z is sine of 1 by z at z is equals to 0. This is again isolated. So a singularity means at that point f is not analytic, but in every neighborhood of that point there is some point at which f is analytic. Isolated means, so at z naught there exists a neighborhood in which f is analytic except at z naught, means in the denoted neighborhood of z naught. Okay, I mean, here one can, so this is an observation, one can So, let uh, f such that omega to c be analytic function, okay, except for isolated singularities, okay. So consider this set. Let us see. Consider this set z belongs to omega such that f has isolated singularity at z. Okay. So my claim is S is a discrete set. Claim is S is a it means that if you take a sequence of points in S which converge to some point z naught, then z naught cannot belongs to S. Okay. I mean this is quite simple because so if you take a sequence of points in S means so if you take a Zn which is a subset of S, the sequence such that Zn converges to Z naught, then Z naught cannot be an isolated singularity, isn't it? Because if Z naught is an isolated singularity, then Z naught is not an isolated singularity of okay, because so if you take any neighborhood of Z naught, okay, that neighborhood will contain one can see the proof of this one. So if you take any neighborhood of Z naught, that neighborhood will contain these points, okay, Zn. So it means that in every neighborhood of Z naught, f has a point of isolated singularity. Precisely that points are these Zns, these Zns, and hence Z naught cannot be isolated singularity of f. Is it clear? Is it clear? I mean, the set of isolated singularities cannot be. I mean, set of isolated singularities is discrete. Okay, so let us look at the non-isolated singularity. Okay, so Z naught is non-isolated singularity. So Z naught is non-isolated singularity if 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 every neighborhood, or one can say deleted neighborhood, every deleted neighborhood of Z naught has a point at which f is not an alpha. Okay. So I mean, for example, one can see fz is 1 upon sine it is 1 upon z. Okay, so what we can say about this singularity? Okay, So let us talk about z is equals to 0. Okay, so if you take like this thing, will be, if your, so you take 1 upon n pi, z is equals to zn is equals to, so this tends to 0. Okay, and at this point f of zn is what? F of zn is basically, so zn is 0, so sin is 0, so this is basically infinity. Okay, so at this point f is not analytic, so f is not analytic at zn. Okay, it means that z, uh, so since every deleted neighborhood, every deleted neighborhood of z equals to 0 contains points 1 upon n pi, and these points f is not analytic, so therefore 0 is an non-isolated, 0 is 0 is non-isolated singularity of f. Okay, so is it clear? Okay, so we'll move ahead. Okay, so isolated singularity are divided into uh, three types. Okay, basically because of the behavior of fz near the point z naught. I mean, you can check the limiting behavior. So let me write. So isolated singularity, let us say z naught. So this is divided into three types. One is removable, one we call pole, the third one we call essential. Okay, so removable means, so basically removable means, so an isolated singularity of f is said to be removable if, so if there exists some r positive and an analytic function g such that, let us say, this ball, okay, in this ball, such that such that gz is basically equals to fz, okay, for 0 in this deleted neighborhood, or, okay, so this is the definition of removable singularity. Okay, so also z naught is pole if limit z tends to z naught mod of fz is basically infinity. Okay, and z naught is essential, it is neither removable, if it is neither removable nor pool. Okay, so this we call as essential. So isolated singularity has these three types. Okay, so the important theorem related to removable singularity is Riemann's removable singularity theorem, which I will write in a general form. Riemann removable singularity theorem. So this is so an isolated singularity z naught of f is removable if and only if any one of the following holds. Okay. What are these following? So first thing is f is bounded in some neighborhood of z naught. Okay, I mean that is there exists epsilon greater than 0 and m greater than 0 such that mod of fz is less than equals to m for every z belongs to z naught comma r minus z naught. Okay, second condition is limit z tends to z naught f of z exists. Okay, and the third equivalent condition is limit z tends to z naught z minus z naught into f of z is basically 0. So if any one of the following condition holds, we say that z naught is a removable singularity. So I hope it is clear. Okay, so let us move towards the pole. Okay, let us look at some analysis on poles. We'll do some analysis on pole. So any doubt in this one? If you have any doubt, you can just ask me. Okay, let us talk some clears. Okay, so let f has pole at z is equals to z naught. What does it mean? That is, for every m positive, there exists some r such that fz is greater than equals to m whenever it's less than r. Okay, this is what we mean by this limit tends to infinity of mod of fz. Okay, at z tends to z naught. Okay, so in particular, what does it mean? In particular, fz is basically not equals to 0 on this ball minus z naught. And therefore, if you consider this function 1 upon f of z on this ball, okay, is holomorphic. Okay. And then z naught is an isolated singularity of G. Okay, but what kind of isolated singularity? So basically, this is removable. Why removable? Because see, mod of fz is greater than equals to 1. So gz is basically bounded by, so G has removable singularity at which point? Z naught. Because this mod of gz is less than equals to 1 by m, okay, and so on this one, deleted neighborhood of z naught, and hence by removable singularity theorem, this one f is bounded in some deleted neighborhood of z naught, then z naught is a removable singularity. So by this one, z, so by removable singularity theorem, this z naught is a removable singularity of G. Okay. Also, one can verify that limit z tends to z naught, gz is 0. Okay. So limit z tends to z naught, gz is basically 0. So now define a function from the whole this ball to C by h of z is basically gz and 0 when z is equals to z naught and when z belongs to. Okay. Now what is this z? Then z is this h. Then h is holomorphic throughout this B. Also, since now h of z naught is basically 0. Okay, that is z naught is a 0 of h. Okay, so what does it mean? This we have seen in the zeros of analytic function. So suppose this, okay, so I will come back to that one. So since h of z naught is equals to 0, it means that there exists an uh, there exists a holomorphic function. Let us say h1 from this ball to C, okay, such that hz can be written like this: z naught to the power m h1z, where h1 at z naught is not equals to 0. So this can be written as for some m, for some. So how do we get this m? So this basically this m is the multiplicity of this root z naught. Basically m, so where m is the multiplicity of z naught. Okay. So now what does it mean? That is, so what is hz? So hz is basically 1 upon fz. Okay. So if you write like this, z minus z naught to the power m into fz is equals to h1z, Okay, what does it mean? It means that z naught is a removable singularity of z minus z naught to the power m f of z. Okay, so earlier z naught was a pole of f. Now there is some m greater than equals to 1 such that z naught is a removable singularity of z minus z naught to the power m into f z. Okay, and basically we call uh, so what does it mean? uh, so this what we have proved. So we have proved something. So this is a kind of proposition which is nothing but, let omega be a domain, okay, and f such that omega to c, let it as be a function having pole at z naught belongs to omega. Then there is a positive integer m and an analytic function g such that omega to c such that fz can be written as z minus z naught to the power minus m into gz. I mean, this is what we have proved. So what is your fz? Fz can be written as like this. So fz is z minus z naught to the power minus m. From here, fz is z minus z naught to the power minus m into h1z, where h1z is analytic. Okay, so this is what we have proved. Also, with this one we have one definition. So we can define now. So this is a definition. If f has a pole at z naught and m is the positive, so m is the I mean smallest positive integer, m is the smallest positive integer such that fz such that such that z minus z naught to the power m into fz has removable singularity at z naught. Okay, then we say f has a pole of order m at z naught. So this is also equivalent of saying that fz can be written in this form. Okay, and the smallest such m, we call it as, I mean, we call it as the order of the pole. Okay, so this is kind of the, this is your M is your order of pole. Okay, okay, so this is regarding this one. Essential similarity we have already seen. Okay, now we'll see the Lorentz series characterization. So it is regarding the classification of isolated singularities using Lorentz series. So I'm just recalling this one. Isolated singularity using Lorentz series. So this is also a theorem which I will not prove because this is already is there in the lecture notes and you can find in any book. Proof is not that much tough, one can do. So let z is equals to z naught be an isolated singularity of f, and let fz is equals to n equals to minus infinity to infinity an z minus z naught to the power n be Laurent series expansion of f in the annulus z such that 0 is greater than mod of z minus z naught is less than some r. Okay, so basically since z naught is isolated singularity of f, it means that it has a deleted neighborhood where f is analytic. So let us say that deleted neighborhood is nothing but this one, and since f is analytic in this one, it has a Lorentz series expansion this one. Okay, so then the first thing is z naught is removable if and only if an is equals to 0 for every n less than equals to minus 1. Second is z naught is a pole of order m if and only if a minus m is not equals to 0 and a n is equals to 0 for all n less than equals to minus m plus 1. Okay, I hope this is clear. This is, and the third thing is says z naught is an essential singularity essential singularity if and only if an is not equals to 0 for infinitely many negative finitely negative integers n. Okay, so here we have defined this one order of the pole. So if m is equals to 1, we call simple pole. Okay. look at this question. I think this is problem 2. So the question is, does there exist an analytic function f from the punctured unit disk, or to C. So f is from punctured unit disk to C. So this one such that f dash has simple pole at 0. So any idea, anyone, how to solve this one? Any idea? Just you can think for 1 or 2 minutes. Just let me know if there is any idea. This is not that much tough. So okay, let us try. Suppose there exists such function. Suppose there exists such function. There exists such analytic function. Okay. So f dash has simple pole at 0. So if you see the Lorentz expansion, so z naught is a pole of order m. Okay. So such function. So f dash has pole of order 1. At 0. So by Lorentz expansion, how we can write this f? So your fz is basically C. Now since f has a pole of order 1, so a minus 1 will be non-zero, other thing will be 0. Okay. So let it write it as something b by z plus summation n equals to 0 to infinity a n z to the power n. This is Lorentz function of f around 0. Lorentz expansion about 0. So this is clear. Oh, sorry. This would be f dash z. Now we can write it as b by z is equals to basically summation n equals to 0 to infinity a n z to the power n minus f dash z. Okay. Let gz is basically summation n equals to 0 to infinity a n z to the power n. That is g is analytic in whole unit disk. Okay, which is nothing but. So since f is sorry, g is analytic in D, it has a primitive because D is simply connected. Okay, so this we have already seen. Okay, so g has a primitive, means antiderivative, primitive in D, say what should we call it as, say h. Okay, that is H dash Z is basically G. So what we will get, B by Z is nothing but this is Gz is n equals to 0 to infinity an z to the power n. So this we can write it as h dash z minus f dash z, which is nothing but hz minus f of z, okay, to the power whole derivative. And this whole thing we can call it as capital Fz. So basically 1 by z we can write it as uh, okay, wait. So just being precise, here we have already solved the problem. So this can be written as, so let's write 1 by z. So 1 by z is basically your b, okay, and this should be whole derivative, okay, and let us call this part, this whole part as this whole part as fz, capital Fz, okay. So it means that capital F dash z, where capital F dash z is what? So F, so this F, so this F is analytic, analytic in this punctured unit is. So what does it mean? This thing means that 1 by z has a primitive in this punctured unit is d minus 0. And we have already seen that this is not the case. Okay? 1 by z cannot have any primitive in d minus 0. So this is a contradiction. I hope this is clear to everyone. Any doubt? Is it clear? This proof? Okay. If there is no doubt, I will move ahead. So, next we are going to talk about meromorphic functions. So the definition is, so let omega be a domain and let omega be a domain f such that omega to c is said to be meromorphic in omega if 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 only singularities of f in omega are either removable, removables, or poles. Okay, is it clear? So the only singularity are either removable or pole. Then we say f is uh, meromorphic in omega, like 1 by z in d minus. So 1 by z in the unit disk. So 0 is basically its pole. So fz equals to 1 by z is meromorphic in unit disk. Okay. Let us consider a problem now. So let's consider this problem. So let omega be z belongs to c such that 0 is okay, and f such that omega to c be analytic in omega, except that the except okay, so except that there is a sequence Zn in omega such that Zn tends to Z naught. Okay. Now the thing is, so that for any W belongs to C, there is a sequence. Let us say, what should we call? Let us say Z and dash in omega with Z and dash also tends to Z naught, and f of Z and dash tends to W as n tends to infinity. So what does it mean? So it means it is saying that you take any point W in C, then there is a sequence in omega which converges to this point Z naught, such that f of Z naught f of Zn will converge to W. Okay, so this we will try to prove. Okay, so suppose there does not exist any such sequence. Suppose there does not exist any such sequence. What does it mean? Then there exists epsilon positive such that mod of fz minus w is greater than equals to epsilon for every z belongs to omega minus this zn. Okay, is it clear? Any doubt? So we are assuming that there does not exist any such sequence which tends to z naught, but fzn does not tends to w. Okay. So now define a function g such that omega to c by, so g of z is basically 1 upon fz minus w for every z belongs to omega minus zn, okay, and 0 when z is equals to zn. Okay, so clearly g is analytic in omega. So how is this so? How g is analytic? Any idea? So what would be limit z tends to any point this zn? Let us say z2. What would be limit z tends to z2? you can see that this this Zn tends to Z naught, okay, and once you take Z tends to any Z2, okay, this Fz will be very close with this V2. Yeah, so you can see that if Z doesn't belongs to this, okay, so if Z is not Zn, this 1 upon Fz minus W is basically what? 1 upon epsilon. Modulus of this is less than 1 upon epsilon. Okay, and once you take any point, let us say Z1, Z2, okay, so since it is very close to W, we have defined it as 0. Okay, whatever I'm saying is clear. Hmm? Okay, this you can let us check and ask me if you're not getting at this point. And mod of Zz is nothing but 1 upon epsilon for every z belongs to omega. Okay, so z naught is a removable singularity of G. Okay, because in the neighborhood of z naught, this is bound. Is it clear? Okay. Yeah. Anything? Okay. So consider. So now we will define another function. Define h from this ball R to C by, so hz is basically your gz when z belongs to this minus z naught, and this is 0 when z is equal to z naught. So h is analytic in this one, okay, and and having limit points of its zeros. So basically hz is equals to 0 for every z belongs to this one. This implies gz is equals to 0 for every z belongs to this z naught. Okay, what does it mean? So this contradicts the fact that f is an allocated except this sequence. This contradicts the fact that f is analytic in omega except at, at a sequence of poles. Okay, so basically in the original case, so these sequence Zn, so these are basically the poles. Okay, so write it down. The sequence that there is a sequence of poles Zn in omega, such that Zn tends to Z naught. Okay. Now we have to show that for any W belongs to C, we can find a sequence Zn dash in omega, such that Zn dash will go to Z naught and f of Zn dash will go to W. Okay. So this is kind of an important thing. Now, is it clear? Okay, so we will move towards the next problem. Next problem is okay. So like since we uh, so suppose f is an entire function, then let me write it down itself. So suppose f is an entire function, then e to the power f of z is also entire, isn't it? But suppose f has a singularity at some point z naught. What we can say about the singularity of e to the power f of z? Okay. The thing is, so the problem is prove or disprove that if z naught is an isolated singularity of f, then z naught can't be a pole of e to the power f z. This is also kind of important thing. Okay. So just look at the solution of this one. So let z naught be an isolated singularity of f. Okay, so since z naught is isolated singularity, what can be z naught? It is either removable, pole, or essential. So let us say first thing is if z naught is removable. Okay, so if z naught is removable, that is by the Riemann removal singularity theorem, we have that is limit z tends to z naught f of z exists, and so limit z tends to z naught limit z tends to z naught gz also exists. Okay, and hence so z naught is removable. So z naught is removable singularity of G. So if z naught is removable, then it is also removable for Z. Now let us look at what if z naught is pole. This is the important thing. If z naught is a pole of f. So in this case, 1 by f has removable singularity at z naught. Okay. So if you define gz as 1 by fz in some deleted neighborhood of z naught, let us say delta neighborhood, and 0 if z is equal to z naught. Okay. So for some delta, for some delta positive. Okay, for some delta positive, Since g of z naught is basically 0, so okay, so what we can write it as g of, if you take this neighborhood mod of z minus z naught is delta. This image will contain a ball centered at 0, isn't it? So this is kind of an open mapping theorem. Okay, this is from the open mapping theorem. Therefore, uh, the range of f, the range of f over this thing z minus z naught is delta contains a neighborhood of infinity, isn't it? Because g is basically 1 upon fz. Okay, and fz contains so g contains a neighborhood of origin. So 1 upon g, which is f, will contain a neighborhood of infinity. So the range of f contains a neighborhood of infinity. That is, what does it mean? There exists r greater than 0 such that mod w greater than r, this thing, is contained in the f of mod z minus z naught is less than delta. Okay, so if this is contained in this one, okay, so since mod w is greater than r is contained in this one, that is, range of f also contains this set w such that r is greater than mod w is less than equals to r plus 2 pi. Okay, which is nothing but, so exponential of this s is nothing but c minus whole 0. Okay, okay, so what does it mean? That exponential of this fz, the range of this one, will be c minus 0 itself for every z belongs to this set. Now what does it mean? What does it mean? It means that z naught is an essential singularity, of gz is equals to exponential of f of z. Okay, and similar thing one can do if z naught is an essential singularity. So it means that if z naught is an isolated singularity of f, then e to the power fz cannot have pole at z naught. Okay, just let us consider one more thing, which is kind of isolated singularity at infinity. So let r be positive and consider this domain omega z such that mod z is greater than r. So this is kind of a neighborhood at infinity. So a function, any doubt? Okay. So a function which is analytic in omega. Okay. So is analytic and omega has, how should I write? So has a, let's say, removable singularity pole, removable singularity pole, or an essential singularity, at infinity if f of 1 by z has removable singularity pole or an essential singularity at z is equals to 0. Okay, is it clear? Okay, so we will solve some problems. Just first thing is, so let f be an entire function. Okay, prove or disprove the following statements. Okay, so the first statement is, so f has removable singularity at infinity, that is, sorry, f has removable singularity at infinity if and only if and only if f is constant. Okay, second thing is, f has pole at infinity if and only if f is a polynomial. Okay, and the other thing is, just let me see. Okay, so let us see this one. So just look at the solution of this one. So first let f has infinity as removable. What does it mean by definition? F of 1 by z has removable singularity at 0. Okay, so consider gz is equals to f of 1 by z. Okay, so since g has a removable singularity at 0, g is bounded in some neighborhood of 0. So, so for z belongs to this, for some r minus 0. Okay, so what does it mean? It means that fz is bounded in some. Okay, so what does it mean? It means that this implies that implies that f is bounded in some domain, say u, z such that mod z is greater than 1 by r. Okay, so that is okay. Now let u complement is basically z such that mod z is less than equals to r. Okay, and since this is compact, so fz is again bounded by something m for all z belongs to u complement. Okay, so here also we can write mod of fz is less than equals to some, let us say m, okay, for all z belongs to u and u complement also. So what does it mean? It means that, I mean, fz is some, let us say m star for all z belongs to C. Now entire function is constant implies, so entire function bounded, it means f is constant. Okay, so this we have proved. So first statement is true. Let us look at the second one. Let's see this one. So let f be an entire function having pole of, let us say, order m at infinity. That is, f of 1 by z has pole of order m at 0. Okay. Now since f is entire, we can write fz is summation equals to 0 to infinity an z to the power n. Okay, this we can write. So let us say gz is equals to f of 1 by z is what? Summation n equals to 0 to infinity z to the power n, z not equals to 0. Okay, since g has pole of order m at z is equals to 0, so a n is equals to 0 for every n greater than m. Okay, and this implies fz is basically, so fz is basically summation n equals to 0 to m an z to the power n. Okay, so this means that f is a polynomial of degree m. Okay, so if an entire function having removal singularity at infinity, it means that it is constant, and if it has a pole of order m at infinity, means it is a polynomial of order m. Okay, I mean, this is a if and only if part. So if you take the converse is quite easy. Here also you can take the converse. If f is constant, then obviously it has removal singularity at infinity. So converse is trivial here in this case, and in this case, if conversely, if f is a polynomial of degree m, so what does it mean? That is, fz is nothing but a naught plus a1z plus a2z square plus and so on am z to the power m. Okay, and let gz is basically f of 1 by z, which is nothing but a naught plus a1 by z, a2 by z square, and so on am by z to the power m. Z is not equals to 0. So z to the power m into zz is basically a naught z to the power m a1 z to the power m minus 1 plus so on plus am. Okay, let h1z is basically am plus a2 z to the power m minus 2 plus a1 z to the power m minus 1 plus a naught z to the power m. So clearly this h1 is analytic. Clearly h1 is nothing but the right hand part of z to the power m into gz. Clearly h1 is analytic, and limit z tends to 0, z to the power m gz is nothing but am, which is non-zero. So this implies that G has pole 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 of order m at z is equals to 0. Is it clear, everyone?
Yes, sir.
Okay. We will just see the last problem. Okay, which is regarding the automorphism. So consider the set. Consider the following set. Consider the set. We will denote it as automorphism of C, which is nothing but F such that C to C such that F is entire 1 1 and onto. Okay. So the thing is proof slash disproof. F belongs to automorphism of C if and only if Fz is basically Az plus B. Okay. So obviously here E is non-zero. Okay. So prove or disprove that F is in odd C if and only if Fz is equals to Az plus B. So observe that if Fz is equals to Az plus B, then obviously it is in odd C. Okay, is it clear? So, so the thing is now since let okay, so let F belongs to automorphism of C. Okay, so what we can say about the infinity? Okay, so since F is an entire function, okay, so infinity has three possibilities. So first is infinity is removable. So in this case, infinity has three possibilities. Okay. So first, suppose infinity is removable. So entire function, if for entire function, infinity is a removable singularity. What does it mean? F is constant, and it means that F cannot belongs to odd C. Hence, because constant function is not in odd C, because it is not on 2, also on 1 1. Second possibility is infinity is pole. In this case, f is a polynomial. F is a polynomial of order m for some m. So if this order m is greater than 2, then f is not 1 1. Okay. So the only thing is in this case which will satisfies is m equals to m, since f belongs towards C. And so polynomial of order 1, what does it mean? So fz is nothing but az plus b, where a comma b belongs to C, a is non-zero. Okay. Now the third thing we have to show that, so this we have shown that uh, infinity is removable is not possible. Infinite is pole. The only thing possibility is m equals to 1. Next we show that if infinity is essential similarity, then that is also a contradiction. Okay. So infinity is an essential singularity. Okay. So by definition, gz is equals to f of 1 by z has an essential singularity at z is equals to 0. Now here we will use the Cassarative-Weierstrass theorem. So by Cassarative-Weierstrass theorem, what we have for every epsilon greater than 0, this image of this deleted, so this star I will write it as deleted neighborhood of this epsilon, come this closure is basically C. I mean, this is dense. Okay. So now consider the set. Let us say D as Z such that mod Z is greater than epsilon, and D dash as Z such that mod Z is greater than M. Okay. Okay, so that is for every M greater than 0, f of D dash is basically C. Okay. Let M1 greater than 0 consider two sets. S1 is equals to Z belongs to C such that mod Z is less than M1, and S2 is basically mod Z, Z belongs to C such that mod Z is greater than M1. Okay. Then what would happen? So clearly f of S1 is open in C, and f of S2 is dense in C. Okay, this is quite clear because of this one. Okay, so now since we have this one, so f of S1 intersection f of S2 is not equals to 5, because a dense set always intersects every open set. Okay, so this implies, so let Z not be an intersection point, intersection f of s2. Okay, so this implies z naught belongs to f of s1. Okay, and also z naught belongs to f of s2. What does it mean? Okay, so this means that there exists something uh, z star belongs to s1. Okay, that is mod of z star is less than m1, such that f of z star is basically z naught. Okay, also since z naught belongs to f of s2, it means there exists some, just say this as z1 star. Okay, there is a z2 star belongs to s2, that is mod of z2 star is greater than m1, is greater than m1, such that f of z2 star is again z naught. Okay, and since z1 star is less than m1 and mod of z2 star is greater than m1, it means that z1 star is not equals to z2 star. Hence, f is not 1 1. Okay, and f cannot belongs to C. Okay, so if any if any entire function has having essential similarity at infinity cannot belongs to odd C. So the only thing which belongs to odd C is AZ plus B. Okay, so we are done. This completes the proof. So I hope it is clear. Everything is clear in this one. So we're done with the today's assignment. Any doubt? One can ask. Any doubt, anyone? So if no doubt, I will close the session and we'll meet for the week 10 assignment. Okay, thank you everyone.
So the
Yeah.
solution for week 8 assignment is uploaded, sir. It in the winding number is an integer only, no, sir.
Yeah, yeah, it is always an integer.
But the answer is given to be it is a real valued function. It is also a correct answer.
Sorry, what? I did not understand.
The answer for week 8 is posted, sir. In that they have mentioned that winding number is a real valued function. It is also a correct statement. They have posted like that.
Ah, yeah, this is a correct statement because set of integer is a subset of real numbers. So they are just playing around the
But
statement.
but a decimal number cannot be a winding number, no, sir.
Yeah, a decimal number cannot be a winding number. They are just saying that winding number is a real valued function. So whatever the winding number gives you, is it a real valued or not? Is it a real number or not? I mean, see, we know that winding number is always an integer. An integer is a real value. So integer is a real number. So that statement is also true.
Oh, okay, sir.
Oh,
Thank
okay,
you, sir.
okay. Anyone else? Any doubt? Okay, so we'll meet in the next live session. Thank you.